Wait. Okay. Well, in the meantime, hello everyone. My name is Lynsey. I work at Slack. I'm a software engineer on the calls team, so on the video conferencing team. We make audio calls and video calls, screen share calls, and something called interactive screen sharing, which is screen sharing, but you can, instead of just viewing someone's screen, you can control it as well. So that makes it really useful for pair programming. And maybe I can tell some jokes. Well, luckily I sort of have this memorized. So, in the meantime, Dan's going to get this working, and it's going to be great. I'm going to talk to you about, first, what is Slack, so you understand why we're making certain decisions that we're making. And then I'm going to talk to you about how we built the product. And then, oh, yes! Cool. I have this slide to help me. So, what is Slack? And the second question is, how did we build Slack calls? I'm going to talk about all these different points. And in each point, I'm going to talk about our first attempt and how our first attempt wasn't maybe the best attempt, and what our second attempt was and what we've learned from that. So at the end of the talk, you might learn what you should do in making your own calling service. But if you don't learn that, maybe you'll learn what you should not do in making your own calling service. So start us off, what is Slack? It's a workplace tool. It's for collaboration, so for messaging, for your apps. You can direct message people. You can have channels around topics that people can talk in. We have a lot of apps available in the App Store, lots of daily active users. So these are enterprise software or corporations that are using our product. And in particular, as I said before, we have video conferencing, so audio calls, video calls, screen sharing, interactive screen sharing, and that's the team that I work on, and that's what I'm going to talk about today. So, how did we build this? To set the stage, we've had an average of 6 developers on the team since the team started 3 years ago. It started with the company Screen Hero. Slack acquired Screen Hero. And then over the next 3 years, we built voice calls, video calls, screen sharing, interactive screen sharing, and now we're here. A little bit about the client. We use Electron. We use Electron's Chromium's WebRTC. So that's a bit about the client side. And with Electron, we get a lot of native features. So as I was talking about before, interactive screen sharing. We layer on a transparent window, which is only possible with the native features that we get with Electron. So I'm going to delve into this first question. Should we do peer-to-peer or have a central media server for our service? So a little bit of review. Peer-to-peer, you have direct connections between 2 users. They send media directly to each other. There's nothing in the middle. The downside with peer-to-peer is that the connections grow quickly. So as you have more people on a call, you have more connections. Instead of sending 1 stream, you're sending 5 to others, and this can grow really fast, really quickly. The other side is having a central media server. I'm calling it a selective forwarding unit here, or SFU for short. I'm going to call it SFU for the rest of the talk. Just means that it selectively forwards media streams on to the other clients. So this is indirect connections. This is really great for when you have group calls, so the connections grow linearly rather than exponentially. So weighing these 2 options, the SFU is better for large calls, works for more networks because we have a stable rallying point for people to connect to. Peer-to-peer has lower costs, we don't have to pay for the bandwidth, and often has lower latency. But in the end, we chose the SFU model, and roll their own server out and people connect to that. But lately we've been doing a reality check. Actually, most of our Slack calls are one-to-one, and peer-to-peer is better for one-to-one. So you can see this is usage from February to now. Average of 2.35 users on a call. So we've come up with a hybrid model. Initial connections send media to the SFU. When the second person joins, they also connect to the SFU. Then these two users form a peer connection, and they keep that channel open to the SFU so that if, say, there were a third person to join the call, these two users can then rekindle that connection, start sending media and receiving media on that connection, and they can close off the peer-to-peer connection. So now we have a hybrid model, so we can have peer-to-peer one-to-one calls, and we can have group calls with our SFU. Our original SFU was Janus. We started off with Janus because it was written in C and C++, and a lot of our teammates had a lot of experience with C and C++. We heavily forked and modified it for our own purposes, and we kind of forked and modified it into a corner where the features that we wanted to add broke a lot of the architecture boundaries. So it was either spend a lot of effort into Janus or write our own media server. So we wrote our own media server called Orca. It's written in Elixir and C++. It's a selective forwarding unit, and it's effective at hunting sharks. Fun fact about orcas, the way that they hunt sharks is they come up from beneath them and flip them over so that the shark can't swim away, and then they can karate chop them from above. So it's fun. So second question, how do we scale and balance load? So we have servers all around the world, in the States, South America, Japan, Australia. We have, I think that's 9 regions and growing. And people find the closest region they are closest to and then connect to that. And we use a simple load balancing algorithm that I'm going to get into next. So in this example, we have 3 Orca servers. They all are saying that they have a certain number of streams flowing through them. And if someone wants to connect, they find the least loaded server in the region, so they ask for the least loaded server in the region, and connect to that media server. Great, connects to the middle one. So what's wrong with this? Well, Slack is a tool for people that usually do work, and people that do work usually operate on a schedule. So let's say at 9 a.m., everyone wants to have a call. And everyone says, hey, what's the least loaded server in the region? And we're like, oh, it's that middle one. Go for it. Connect to it. And everyone connects to the least loaded server in the region in a very short amount of time, and then it's overloaded with streams. Not good. Another example, say we have the same 3 Orca servers. I don't know if you can tell, but the one on the left is unhealthy. It's an unhealthy Orca server. For whatever reason, it's not accepting media connections. And it drops all of its TCP connections and has no more people on it. So we lose all our media connections to that server, but for some reason, its outgoing TCP connection to our director is saying, hey, I have 0 streams and I'm okay. And everyone connects to that one. That's unhealthy. Not good. Now all our new calls are directed to the bad server, and our region has effectively gone down because of one bad server. So that's also not good. So a quick solution, we can randomly pick from n least loaded servers, and if one of them is bad, then at least maybe we have a chance at getting a good one. So that's a quick solution. So the guy on the left is bad, maybe we'll pick the guy on the right. because we're not necessarily always going to that one. In the future, we're hoping to do multi-server calls. Better for load balancing. We don't have this problem of everyone going to the same one. We can just disperse everyone as they see fit. And it actually it could use the private fiber, which might be faster than peer-to-peer, which would be better for everybody. Next question. How do we deploy Orca code? So in our deploys, currently we have two sets of servers. So we have our old sets of servers, and we want to deploy some new code. So we bring up a new set of servers, blacklist the old set, so nobody else could connect to the old set, and wait for all the calls on the old set to die out, and have everyone connect to the new set. This is really long. It can take up to 24 hours. It can be a little bit more expensive because now we need two sets of servers. And if people are taking too long, we cut them loose. Say, nope, not anymore. We need to deploy our code. So that's not so good. So in the future, we want to do call migration. So the idea is that you only need one extra server rather than a whole fleet. So that's cheaper. And it would be a faster deploy. So in this case, we have the blue representing all the clients that are connected to an Orca server. They're connected to the one in the middle, which is an old one, and they reconnect to a new Orca server, just kind of like in the peer-to-peer to SFU transfer. They transfer over to the new one. And once everyone is transferred over, we kill the old one, and then bring a new one up from the old Orca servers to do the same thing. And now we only need one extra server. Next question, how do clients connect to our media servers? So this was our original model. A client connects to Orca, so we have our SFU on the same box as a turn box. We use port 22466 for media traffic for UDP, and we figured having just one port open would allow everyone to make their firewalls a little bit easier. They only have to be open for one port. Turns out that's not good enough for some people. Some enterprise firewalls actually block UDP. So what did we do? We allowed TCP as a backup. So now clients can send their media over UDP or TCP. Still wasn't good enough for everybody. Some very strict firewalls, they don't allow traffic to any port but 443. So we use HA proxy at the front to deal with signaling. And if the client can connect media over UDP or TCP to port 22466, we do that. And if they can't, if the firewall blocks it, then they can send media to port 443. Next question. How did we write a media server in Elixir and C++? So I guess a better question first is, why did we write a server in Elixir and C++? A little bit about Elixir. It's an extension of Erlang. It's a functional programming language. One reason why we chose it is for the crash tolerance. So in this example, we have a supervisor process that sits at the top. It spawns more processes, and those processes spawn processes beneath it. If a process at the bottom dies, it doesn't affect any of the other processes. They aren't affected, which is really great for calls, because if those are users connected to a call, their process doesn't die when someone else causes a crash. Another benefit is it's easy to write code. So this is a snippet from our server decoding an RTP packet. You can see just in the function definition that we've parsed the header into different variables, which makes it really, really nice. So here's a diagram about a little bit about the architecture. We have the C++ side on the right and the Elixir on the left. This represents the flow of a media packet going through the server. So the number crunching needs to happen in C++. Things like bandwidth estimation, forward error correction, decoding and generation, encryption and decryption. That all needs to happen on the C++ side because the C++ is better at handling the heavy number crunching sort of things. And then we put all the application logic in Elixir, so users joining, signaling, room logic, pub sub, that sort of thing, stats reporting is all in the Elixir side. So how does this actually perform? So in this example, we were doing some tests with, we had 13 audio and video calls of 5 participants each. On the right is the media path again. So we have what happens when a media packet goes through Orca. Well, it gets decrypted, there's some bandwidth estimation stuff, then it gets sent to Elixir. The pub sub sends it to the right people in the call, then it goes back to C++, and then it gets encrypted and sent on its way. So this is actually timing how long it took for media packets to get through Orca. And you can see the decrypt stage pretty fast, 0.5 milliseconds, something like that. The 2 Elixir, a little slower, about 8 milliseconds. Pub sub also slow, and C++ not so good. So in this, we're trying to find the bottlenecks. We're asking ourselves, how do we make this service better? Where are the bottlenecks? How do we make it faster? So this is about 600,000 media packets after 30 seconds. This graph is after 90 seconds, the same test. So from 30 seconds to 90 seconds, you can see the numbers getting larger over time. It takes longer for media packets to get through the media path. And again, it's the 2 Elixir, pub sub, and 2 C++ that's taking a long time. So going from C++ side to Elixir, doing the pub sub in Elixir, and going back to C++ is our bottleneck in this case. We did some more load testing, this time with 5 audio and video calls of 10 participants each. This is more streams. So in the previous case, we had 325 streams. This is 500 streams. And you can see again, the 2 Elixir and pub sub are pretty heavy on the P95 and the P99. And that spikes our total. So we're finding these bottlenecks through running these tests. And again, after 90 seconds, still higher yet. So that's not good. So our next step in this is, how do we fix this? And it looks like how we fix this is figuring out this 2 Elixir pub sub and back to C++ ordeal that we're doing currently. So what we're going to do in the future, seems like the best bet is to put the whole media path all in C++. The downside of this is it makes the crash isolation that we talked about before is only per room rather than per user. So it means if one user on the call causes a crash, the whole call crashes, rather than if a user causes it to crash, then it's only that user. So putting these parts in C++ might allow the media path to be a little faster and get our media packets through a little better. Another question, how do we monitor our Orca servers? One really reliable thing we've been using is Grafana alerts. Our servers report any large spikes, or they just report disconnections. And if we have any large spikes and disconnections, then we know something's wrong. Servers do self-check-ins. We have internal monitoring. We have external monitoring. Constantly making sure that our servers are healthy. I want to talk about self-check-ins, why self-check-ins are not always reliable. This case, if you have an Orca server on the left that says, hey, I'm healthy, checks into our check-in director, it might not actually be healthy. And we've had a case where we've said, oh, we've detected that the server is bad, so we've blacklisted it, took it out, and then the server's like, oh, hey, I'm healthy, check-in directory's great. Okay, let's send people to it. And now we have a zombie Orca server that just keeps coming back alive again, even when we're trying to shut it down. So not always relying on self-check-ins, a good idea. Next, I want to talk about other calling services in Slack. So Slack calls is not the only calling product that you can use in Slack. You can actually initiate calls with any other service that you want. That, for example, you could start a call with appear.in in the Slack application. We also integrate with Google Hangouts and Skype. The choice lies with the user, so they can enable calling in Slack. The admin can change the settings so they can use whatever calling product they want. And so we're not trying to compete with all these different calling applications. We're just providing an option for our users. And we actually really want to build out this API so it's very public, and we can have deeper integrations with calling applications. So if you have a calling application and you're interested in using Slack's calling API, come talk to me. We're working building it out pretty soon, so it'd be good to get input on that. To recap, talked about what Slack is and all these different hurdles that we've gone through in building the product of Slack calls. I hope that you learned something about how to build the service, or maybe something about what not to do in building the service. And that's it. Thank you. Cool, we got lots of time. Yeah, we'll do questions.
How to ask it diplomatically, but was Elixir a fail then?
Not quite. It's not good for the media packets. Maybe if we could have done it all again, maybe we would have chosen Go. But it's been really great for the application logic. It's been really fun to write it in. Having our server not totally go down when one thing crashes is also amazing.
So you move media part processing out, but keep the more high-level application stuff in.
Yeah. Keep the high-level application logic in. Yeah.
So you mentioned you use Grafana for server-side monitoring. What do you use for client-side monitoring?
Client-side monitoring? What do you mean?
Like your clients that are connecting to the Orca servers, like for example, the browsers or Electron.
I see. I guess if they're not connecting, that's getting reported to our stats. We have a data warehouse. I guess that would go to our data warehouse. Let's see. Orca might detect it if a lot of clients aren't detecting. If certain ones aren't connecting, we won't detect it until later. So if nobody's connecting, we'll get our external monitors to go off. And if it's some subset of users, we'll have some kind of after the fact data on which users those were.
You mentioned AWS and Google.
Mm-hmm.
What was the rationale for having both on the books, and is one
We have both because if one goes down, we have the other one. There's a possibility that a certain company is like, I don't want to use that company's server, so we have that option. That hasn't come up yet, but it could. But basically for stability is the reason. And as for performance, we haven't noticed the difference between the two.
There's only one cloud infrastructure provider who has infrastructure in Southern Africa, so how about Microsoft?
Microsoft, I feel like we wouldn't go with them because they're a competitor in Microsoft Teams, so. But who knows? Oh, sorry? About the motivation to do the calling.
Coding and encoding.
Oh, okay. The coding and encoding on the. Sorry. Like, let's go back. So I'm gonna. Okay. Yeah. Any other questions?
You were mentioning about integration, Slack and other applications for calling. Do you have any plans to integrate with community software like Asterisk and Research yourself, or you're expecting the community to go ahead with that integration, if it's possible?
We would open up our platform API so that they could integrate with us, and then have a richer, deeper integration. I'm not sure if they have an integration with us. There's some basic integrations that are available right now, and I'm not sure exactly what that list is. But yeah, if it's once it's publicly available, then anyone can use it.
Is it publicly available at the moment?
It's It's not. We've worked with different clients to get it into our Slack app, but we want to make it public so that everyone can.
What's the requirements for a company to approach you with regards to integration?
I'm not sure. I guess that's the platform team that does that. But hopefully very soon there won't be any requirements of approaching or something. Anyone can just have a calling application in Slack.
Can you tell a bit more how this third-party integration is working?
Well, right now, so example with appear.in, you can hit the call button, and instead of launching a Slack call, it would launch a different call with appear.in, and that might post an object to channel, and then people can join it. On the bottom, we have this call object that is for Slack calls, and it would be nice if anyone that had a third-party integration could tap into that and have a richer UI experience, so show avatars of people that are on the call. I don't know if you noticed, but all these avatars are Game of Thrones characters. So that's what's available right now.